Hydrocarbons is going to be the topic of this first lesson in a chapter on organic chemistry here, and we're just going to really introduce the subject. In college, students take an entire year of organic chemistry for many a major, and not just chemistry majors at that. And in this case, we'll first start by introducing what exactly organic chemistry is. We'll then move on and talk about hydrocarbons, which are compounds made of only hydrogen and carbon, hence the name. And these are going to fall into four classes: alkanes, alkenes, alkynes, and aromatics. We'll talk a little bit about each of those four classes, and then we'll conclude the lesson by going into some of the molecular structures and the different molecular representations we use for describing these hydrocarbons. Now, this lesson's part of my high school chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post a new lesson or when I get to posting a new playlist, subscribe to the channel and click the bell notification. So let's start this lesson by first talking about what exactly organic chemistry is. And the word organic has gotten pretty popular over the last couple of decades, and people use the word to describe food that is grown without pesticides and all natural and all this stuff. And that's not exactly what we're talking about here when we talk about organic chemistry. So it turns out that organic compounds are carbon-based compounds, and organic chemistry is going to be the study of the chemistry of carbon-based compounds. And these are important because all of life is based on carbon-based compounds, these organic compounds. Now, we also find these organic compounds outside of living organisms as well, so don't think that living organisms have the monopoly on them, but these organic compounds are the basis of life as well. So that's their importance here, and they're carbon-based, and that's going to be important as well, and we'll see what makes carbon so special in a minute. So, but it's not only carbon, it's mostly carbon, hydrogen, oxygen, and nitrogen, and you might see some halogens, and you might see some sulfur and a few other trace elements and stuff like this. But it's mostly carbon, hydrogen, oxygen, and nitrogen, and mostly carbon and hydrogen. And that's why this first lesson on hydrocarbons will be appropriate, because those will be compounds that are only carbon and hydrogen. It actually won't have any of the other nonmetals, just carbon and hydrogen. We'll see what those mean in a minute. Now, carbon is unique to being the building block of life here. So because it's really got some flexibility in the structures it can form. And so it turns out carbon has 4 valence electrons, you know that. And with 4 valence electrons, it can form 4 bonds in trying to get a filled octet. And also, because carbon is small, it actually can form double and triple bonds, form pi bonds, very readily. And this gives it a lot of options, a lot of flexibility that can contribute to the complexity of the molecules we see in life. And so, if you take a look here at carbon, carbon might be involved in making 4 single bonds, in which case it would be an sp3 hybridized atom with bond angles of 109.5 in a tetrahedral structure. So, but you might also see carbon making a single double bond in a structure and then 2 single bonds, in which case that carbon would be sp2 hybridized, be bond angles of 120 degrees, and it would be trigonal planar in its geometry. You might also see a couple of other options, either carbon making 2 double bonds or carbon making 1 triple bond and 1 single bond. In either case, that carbon would be sp hybridized, and the bond angles would be 180 degrees. The molecular geometry there would be linear. And all of these are present somewhere in the variety of organic compounds we know, as including in living organisms as well. So it's this great variety. We don't see this with like nitrogen, which typically only makes 3 bonds, or oxygen, which only makes 2 bonds, and there's just not enough variety there for those to be the basis or the building blocks of life and stuff like this. And we might envision that maybe silicon, which is right below carbon on the periodic table, that maybe silicon could be the basis of life. And the big problem for silicon is that while silicon can also make 4 bonds, again having 4 valence electrons and being 4 short of a filled octet, so it turns out that silicon is quite a bit bigger than carbon, and as a result, it doesn't make pi bonds very well. It's just too big to have sideways overlap of the p orbitals from side to side the way carbon does. And as a result, if it doesn't make double and triple bonds, then no pi bonds very well, then you're really limited on the type of structure you might see for silicon. And as a result, we don't know of any silicon-based life at all. And so at this point, really carbon is the building block of all of life, and we start looking at other planets to see, are they capable of, sustaining life? Well, one of the things we do look for is carbon. And, it turns out water is really important as well. And there's some other characteristics we look for, but carbon really obviously central to this particular lesson. All right, the first class of hydrocarbon we're going to talk about are the alkanes. And the hallmark of an alkane is that all of your carbon-carbon bonds are single bonds, not double bonds, not triple bonds. Now, these are going to come in three varieties. They might come in a straight chain alkane, where you just simply have a linear chain, a linear continuous chain of carbon atoms. It might come in a branched alkane, in which it's not a straight chain, but you've got branches coming off the interior somewhere. And there's also something called a cycloalkane, where you actually get a ring of carbon atoms. Now, when you've got the straight chain or the branched alkane, it turns out, these would be what we refer to as being saturated. And in this case, in organic chemistry, saturated means something very specific. It means you have the maximum number of hydrogen atoms possible. And it turns out every time you form a ring, you're going to kill two hydrogens. Every time you form a carbon-carbon double bond, or any kind of double bond, truth be told, or triple bond or something like that, any kind of pi bond, it actually reduces the number of hydrogen atoms in the molecule, just a structural feature there. And so any molecule that either has rings in it or that has pi bonds in it would therefore be termed unsaturated. And we'll see that's one of the characteristics of the alkenes and alkynes we'll study in just a little bit. Now, these alkanes, it turns out, are pretty, unreactive. They're not the most reactive things in the world. There's not a whole lot of chemical reactions they do. However, they are combustible. So it turns out gasoline is a mixture of medium chain alkanes, we say, and stuff like that. And you can react it with O2 to produce CO2 and water. That is combustion, and that's what powers your internal combustion engine. So, but outside of combustion, there's not a lot we do with alkanes. It turns out you want some differences in electron density, which usually you get when you've got some differences in electronegativity in a molecule. And with carbon and hydrogen being very close in electronegativity, so there's just no big differences in electron density in the molecule, and that means that these are going to be fairly unreactive outside of combustion. All right, so now let's take a look at some of the other classes for hydrocarbons, and we'll start with alkenes here. And alkenes, the characteristic that we've got this carbon-carbon double bond right here. And it turns out with a double bond, you might recall that's one sigma bond, one pi bond. And it turns out that the presence of pi bonds makes these a little more reactive. It turns out their characteristic type of reaction is called an addition reaction, where you exchange the pi bond for a new sigma bond attached to each of these carbons. And there's a variety of options of the different bonds you might make and stuff like this. So the key is that the presence of a pi bond makes these a little more reactive. And whereas alkenes have a carbon-carbon double bond, an alkyne is going to have a carbon-carbon triple bond, and these also have a little added reactivity associated with them as well. And so we see that with alkenes and alkynes, these added pi bonds give them a little extra added reactivity, which is going to point out something unique for what we call aromatic compounds, or just simply aromatics. And the most famous aromatic compound of all time is benzene here. And benzene is a 6-carbon ring, and we often draw it out with alternating single and double bonds all the way around the ring. So, but it turns out you could draw this two ways. You could have the double bonds in these three locations or in these three locations. But it turns out these are actually just resonance structures of the same thing. And you've got delocalization of the pi electrons going all the way around the ring. And so oftentimes we actually draw this with an entire conjugated ring of electron density. And so you'll commonly see benzene drawn this way. And so benzene is not the only example of an aromatic compound, but it is by far the most common. And any compound that's got, a benzene ring in it would be termed an aromatic compound. Now, the unique thing here is that this delocalization of these pi electrons actually makes them super, super stable. And so benzene rings, they do not do the same addition reactions that you see with alkenes and alkynes. And so with alkenes and alkynes, those pi bonds actually give them extra reactivity. But it turns out in a benzene ring, in the aromatics, it turns out they're really stable. And it's related to this ring-like structure and the fact that it's conjugated and delocalized. So, but the reason is not so important, but understanding that they're pretty unreactive. The types of reactions they do, you have to actually add pretty reactive reagents and stuff like that, but not nearly as reactive as the alkenes and alkynes. Cool, you should notice that all of these do have pi bonds, and having pi bonds, they don't have the maximum number of hydrogens like the straight chain and branched alkanes would. And whether they've got a ring or not, like the aromatics, but they've all got pi bonds, and they're never going to have that maximum number of hydrogens. And so we say that these are all unsaturated. So, and it turns out, again, this idea of being unsaturated, so you're probably familiar with the term of saturated fats and unsaturated fats, and it turns out a saturated fat is one where just you have all carbon-carbon single bonds, whereas an unsaturated fat is actually going to have a carbon, at least one carbon-carbon double bond somewhere in its structure. And a polyunsaturated fat would have more than one carbon-carbon double bond. So just want to get that idea across of saturated versus unsaturated. A saturated hydrocarbon has the maximum number of hydrogens possible, and that happens with straight chain or branched alkanes. And then an unsaturated hydrocarbon is not going to have that, and that typically happens with either the presence of a pi bond or the presence of a ring. All right, so now we want to look at some of the different molecular representations we use in organic chemistry. And we're going to start with the structural formula, and the most common one you'd be familiar with is the Lewis dot structure. But there are also other types like the line angle structures and things of this sort. And it turns out you're going to find out that organic chemists are some of the laziest people on Earth. Not really. So, however, drawing a lot of these structures gets really repetitive. And because they have so many carbons and hydrogens, we often come up with shorter ways of drawing them out. And one of these is the condensed formula. So in this case, if you look at this structure right here, it turns out this is pentane, and we'll learn how to name that in the next lesson. But in this case, another way to represent this would be to simply write the carbon, the first carbon you see, and then say how many hydrogens it's attached to. And then go to the next carbon in the chain and state how many hydrogens it's attached to, just 2. And do the same thing all the way across. And so you start off with a carbon bonded to 3 hydrogens, and then you've got 3 carbons in a row that all have just 2 hydrogens, and then finally you've got the last carbon that's got, once again, 3 hydrogens. So, and it's a lot easier to draw this than to draw the entire Lewis structure. We call this a condensed formula, whereas this was a structural formula. Now, we can make these condensed formulas even faster. So it turns out with these CH2s, when you got long alkanes, long straight chain alkanes, you often get a lot of these CH2 groups, and so instead of drawing the whole thing out, sometimes we'll get even lazier, and we'll just put that CH2 in parentheses and just say how many times it's repeated. In this case, it was 3 times. And so we get even lazier. So, and if you ever learned line angle structures in the future, we won't cover them in this class, we get even lazier. We just even stop drawing in the carbons and hydrogens in weird ways. So they're just so prevalent, they come up with ways to represent them. So cool. Now the last thing is the molecular formula, and this is one you'll be familiar with as well, which just simply states how many of each atom you have. And so in this case, we've got 5 carbons, and in this case, 12 hydrogens. So 3, 5, 7, 9, 10, 11, 12. Cool, and that's just your molecular formula. So the Lewis structures you would have seen before, obviously, and the molecular formula. So, but I wanted you to see the condensed formula as well. Now, it turns out from a molecular formula, there's a lot of different isomers that would be possible. Like, is it a straight chain alkane? Is it a branched alkane? Things of this sort. But once you draw a structural formula or one of these condensed formulas, it's going to key in on which particular structural isomer you might be referring to. So they're much more specific in elucidating the structure of your hydrocarbon. All right, so I want to work through one more example with you here. And instead of a straight chain alkane, here we're going to have a branched alkane. And so things are going to be a little bit different, but we'll start the same way. In this case, in the middle of the molecule, we don't have a bunch of CH2s repeating anymore, so we're not going to, put a bunch of CH2s in parentheses as an option here, like we did in that first example. So, but we'll start from the left-hand end, and we've got a carbon, and that carbon is bonded to 3 hydrogens. Then it's next to a carbon here that's bonded to 2 hydrogens. So we'll write CH2 right next to that. And then we've got this carbon here that's only bonded to 1 hydrogen, so we're going to write CH. And then we go continuing on down the chain, CH2, CH3, except we've got this branch here. And the way this works with these condensed formulas is if your branch is a single, you just write it next after the H. But if it's got many atoms, as this guy does, this is a CH3 group, you're going to put that in parentheses as well. And then go continuing on back down the chain, CH2, and then C with 3 H's, CH3. And that would be a proper condensed formula. And what you'll notice is that there's actually 2 different situations where we use parentheses, which can make it a little confusing. You can either use it for CH2s, and when you see a CH2 in parentheses, it means number of repeating units. But if you see anything other than a CH2 in parentheses, it means it's a branch coming off the chain, and you've got a branched alkane instead of a straight chain alkane. Cool. Finally, we've still got a molecular formula here, and here we've got 1, 2, 3, 4, 5, 6 carbons. And if you count up all those hydrogens, you'd see you've got 14. So 3, 4, 5, 6, plus 3 is 9, 10, 11, 12, 13, 14. Cool. And there's your structural formula, your Lewis structure, your condensed formula, and then finally your molecular formula. Now, if you found this lesson helpful, would you consider giving me a like and a share? One of the best things you can do to promote the channel and make sure other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you are looking for practice problems on organic chemistry for your high school chemistry course, check out my premium course at chadsprep.com.